flutterby, butterfly, on velvety wings in the warm summer sky.
And you are of course most welcome. This is Project Euler problem number 35, circular primes. The number 197 is called a circular prime because all rotations of the digits are themselves prime. There are 13 such primes below 100. How many circular primes are there below 1 million? Okay, this is fairly simple, and as usual I will go through a brute force solution, a more elegant solution, and then a more optimal solution. So, and as always for the optimal solutions, you've got to kind of think outside the box. So, first import from time import time. You don't need this one, I just like to time my algorithms. And then from SymPy import, what are we importing? Oh yeah, is prime. Is prime. There we go. Now, if you don't have SymPy, you can either borrow a prime function off the internet, or you can build one of your own if you're really brainy. I'm not brainy, and I'm not going to reinvent the wheel, so I've got SymPy, might as well use it. So, the brute force solution basically does what it says on the tin. We're going to go through every integer from 2 up to about 1 million. We're going to see if it's a prime number, and if it is, we'll see if it's a circular prime, and if it fits both criteria, then we add 1 to the total. So, little something like this. Def brute, and we're going to have circulars equals 0, so we'll have a counter, and then for I in range, we'll start at 2 and we'll go up to just shy of 1 million. Then we want to, oh yeah, if is prime I and is circular I, then we add 1 to the total, so circulars plus equals 1, and then right at the end we return circulars there, and we're going to want to print this out, so print brute. There we go. Right, so now we have to work on this is circular method, and there are many ways to skin this particular cat, and I've chosen the most convoluted for some reason. So is circular, we're inputting a number here, so we'll say I. Now how exactly we're going to do this, I've completely forgotten. You can use string manipulation and slicing if you want, but I don't want to keep converting this number to a string and then back again. So what I'm going to do instead is do a bit of mathematical magicry. You know what I mean. So the first thing we need to do is for j in range. So we're going to need to do some rotations. So let me show you what we're going to do. Let's pretend that 1379 is a prime number. I don't know if it is. We'll just pretend that it is. This is what we're going to do. So we take this 9 that's on the end. We're going to remove it and then place it at the beginning using mathematics. And then we check if this is prime, and then take the 7 off, put that at the beginning, check that, take the 3 off, put that at the beginning, check that, and now we've made 4 checks, so that's all we need, because now we're back at the original number. So the number of rotations is exactly equal to the number of digits in the integer. So for j in range, we are going to need to get the length of the number. So what I am going to do is s equals length of the string of I. I think there's a mathematical way to get the number of digits in a number, but I've completely forgotten what that is. So we'll just go with this. So for j in range, 0 s. That ensures we get the right number of rotations. So if we find a number that isn't prime, then this isn't circular. So if not is prime I, then we simply escape the function. So return false. If it is prime, then we generate the next rotation. So we need to get the last digit. So I'm going to say that's D equals I mod 10. That will give you the last digit that we're going to place at the start of the number. Now we need to store the other digits. And we do this thusly. So n equals I integer divide 10. So that splits the number up into the last digit and the other digits. Now we're going to take the last digit and put it at the beginning. Thusly, I equals D times 10 to the power of s minus 1, and then we add the other three, the remaining digits, so plus n. Trust me, it works. I am going to have to rearrange this slightly because I want it to give the right result. So a bit of BibMass here, and I think if I do that there and that there, that should be correct. Now if we escape this loop without returning false, then the number must be circular. So if we get to this stage on line 13, I'm going to put return true. So that is pretty much all the code we need, I believe. So what I'm going to do now is give it a test. So start equals time, and in here we're going to put time minus start. If we run this, it should give the correct answer, but it will take a while. That really is taking a while. There we go, that's the correct answer, and it gives the answer in 6.93 seconds, which is pathetic. So there are many ways we could improve this particular algorithm, but I'm not going to bother because it's not really going to help much. There are much better ways of doing this, and I'm going to discuss one of them with you right now. Let's go down here a bit, shall we? Yeah. Okay, so the first method I thought of was to do a little bit of whittling down. So if you look here, what we're essentially doing in this block of code here is searching every single number to see if it's prime. Now this is obviously a waste of time with the even numbers. So there's a big old saving we could make there. So instead of testing every number to see if it's prime and circular, why don't we sieve the primes and just test those? So step one of this new algorithm is to sieve out the primes, because we only want to test the primes. Now the second step, now you probably noticed this, in order for a prime to be circular, it cannot contain any even numbers or 5, because if we have a number like this, let's say 1927, again I don't know if this is prime, but let's say that it is. If we rotate this once, we get 7192, which isn't prime. So any number with a 0, 2, 4, 5, 6 or 8 cannot be a circular prime. So as well as sieving out the primes, we're then going to sieve out all the primes with undesirable digits. I'm not a mathematician, so I don't know the terminology here. I've just put undesirable digits. So there we are. And then third pass is to, so the point of the first two steps is to build a list of candidate primes, and then in the third step we check for circularity. And that should save a fair bit of time. So I'm actually going to open a new file, and we're going to see if we can make this work. There we go. Okay, so this is going to import some of the bits from the other algorithm, so I'll just copy this. So we want the isCircular function, and we want the same imports, so I'm going to pop those there. So we are going to perform a prime sieve using the sieve of Eratosthenes. So def sieve, and we will need to feed in a limit. Now I have explained the sieve of Eratosthenes on a couple of previous videos, and I'm not going to do it again, so if you don't know what the sieve of Eratosthenes does or how it works, Google is your friend. So sieve, and then we create a list of booleans all set to true. So primes equals true times limit, and then we've got to set 0 and 1 to false. There we go. And then the next bit, I keep forgetting. Alright, so we need a divisor, d equals 2, and then we do while the square of the divisor is less than the limit. And then we use our divisor to find the non-primes, thusly. So if primes d, if the current divisor is a prime, then we're going to go to all of its multiples and mark them as false. So if primes d, then for I in range 2 times d, we don't want to mark d as non-prime, 2 times d, we're going up to the limit, and we're going up in increments of d, and then we mark all the indices as false. So primes I is false. There we go. Then we increment d when we need to, and then we return primes. So that's the sieve of Eratosthenes, as simple as I can explain it. So that's the first pass. Now the second pass is to get the list of candidates. So we want to kick out all the primes that have 0, 2, 4, 5, 6 or 8. And the way to do this is thus. Def get candidates. I should move this to the top actually, shouldn't I? Oh, no, there's a better way to do this actually, I've just discovered. So get rid of this, and we get rid of this, and that's saves on a bit of clutter, doesn't it? So get candidates. Oh, and we're feeding in the sieved list of primes, so I'm going to put primes there. So we need a list of candidates, so candidates equals the empty list, and then d, so this is going to be the list of digits that we don't want, that we want to kick out. So but for this to work, we are going to have to convert each number into a string. So 0, 2, 4, 5, 6, and 8. There we go. So then for I in range 2 up to 10 to the 6th, Then we convert the current number into a string, so s equals stri. That's going to make the next step a bit easier. If primes I, so if the current number is a prime and not any, now this is not very readable code, but it does work, trust me. N in S for N in D. Okay, so what is this code doing? This looks funny, doesn't it? So if the current number is a prime and if the current number does not contain any of these digits, that's essentially what this code is doing. If it passes both criteria, then it becomes a candidate and we add it to the list. Candidates.append I. And then right at the end, return candidates. Okay, so this function generates the candidate numbers, which we then pass on to the third function, which is get circular, and that takes in candidates. So this function is pretty simple. We're just going to start with circulars equals 0, and then for candidates in candidates we check if they're circular. So if is circular I, if it is, then we add 1 to the number of circulars and then return circulars. So a bit more involved, this one. So we're going to do print. Oh, then we need to write another function for the next bit. So let's get rid of this and get rid of this. Def p35 dynamic, let's call it. We're not going to feed in anything. We're just going to spit out an answer. So primes is going to be the sieve. So sieve, I will feed in the number 10 to the 6. So primes is going to be that, and then we need to feed in the list of primes to the get candidates function. So candidates equals get candidates primes. Yep, and then once we've got the candidates, we then check for circularity. So it's circular equals get circular. For that we feed in the list of candidates. And in fact what I'm going to do here is just print off get circular. There we are. So if we run that, we should get the same answer but in a bit less time. We don't need to print because we're calling print up there. Silly me. There we go. Let's see if we want to get the time as well, don't we? So up here, start equals time, and down here time minus start. Okay. Now it doesn't like this. Identified 9 P35 candidates. Oh, it's P35 dynamic. There, are you happy now? Good. Right, let's go. See if this works. Oh, name I is not defined, so that was in if is circular. Oh, yeah, that should be candidate. Right, try that again. Yeah, we get the correct. Oh, no. Now there's a very good reason why this didn't work. Because if we go here, it's going to kick out the 2, isn't it? Because, yeah, it's going to kick out the 2, even though it is circular. So I'm going to put 2 here, bit of a cheat, and we should now get the correct answer. Yeah, 0.96 seconds, so quite an improvement. But there is another way of doing this that knocks the spots off both algorithms, and I'm going to show you it now. I'm going to talk to you about something called a Cartesian product. So the two solutions that I've discussed so far suffer with the same problem. They both at some point loop through all the numbers between 2 and a million and figure out whether or not they're prime, and then if they're circular. A better way might be to generate only those numbers that contain the correct digits. So all the numbers that are circular are basically combinations of those 4 digits. So I did look at itertools, permutations and combinations, but they did not provide much help. So for example, permutations, the order doesn't matter. So 13 is a permutation of 1379, and so is 31. These are counted as separate permutations, but it only uses each digit once, which isn't really what we need, because we might have a number like 113 or 997733, something like that. So permutations doesn't really help. Now with combinations, it's even worse, because 13 and 31 are counted as the same combination. So it won't give you both of these answers, it'll give you 13 and 13. It'll just give you 13 once, I think. So that's combinations and permutations, but there is a third option provided by Python's itertools module called product, and this gives you the Cartesian product of a set up to a number of specified elements. So let's say we want 1379 and we want a set of 6 elements. So it could do 1 1 1 1 1 1 1 1 1 1 1 3 1 1 1 1 1 7, so on and so forth. It will just generate every possible combination using the number of digits that you specify. If you want something with 3 digits, it'll go 1 1 3 1 1 1 1 1 7 1 1 9 1 3 1, etc., etc. So product is what we're going to use. Now for this one, I will be using the circular method, so I'll copy this in. There we go. And we are going to need itertools from Python's library. So from itertools, import product as p, because I'm feeling very lazy. Right, so there we got the isCircular method. I've already shown you that a couple of times, so we'll leave that. And then the next thing to do is set up the other method. So def p35 best doesn't need any inputs, so we will have to take account of the 2 and the 5, which are prime and circular but will not be included in these calculations because we're only working with 1 3 7 and 9, so these need to be hard coded. Okay, nums equals 1379. This is the string that we're going to be working on, and then we do this. For I in range 1 to 7, we want all possible combinations of these digits, but we want all the numbers from, 3 up to a million. So we're going to start with 3, 7, 9, 11, 13, 17, 19, 31, 33, going on like that. So we start with getting all the 1-digit products, then the 2-digit products, then the 3 digits, then the 4 digits, and all the way up to the 6-digit products. I hope that makes sense. In fact, I'm not going to put this up there. It might get confusing because we've got lots of letters down here. So for P in product, and first we put in the string that we're going to be working on, and then we put repeat equals I. And then this is what we do next. So we're gonna, what this is actually going to return a what do you call it, a tuple. We need to convert the tuple into a string and then convert the string into an integer. So we're going to do this. Int, and then join, and then we have a bit of comprehension going on here. So j for j in p, that gives us an integer, and then we do if is prime n and is circular n, then we count it. Then it goes answer plus equals 1, and then right at the end we return answer. Why doesn't it like that? Undefined name answer. Oh no, it's like being slow for some reason. Right, okay, that's done. So then we do print p35 best. We want the time as well, so let's make this here. Start equals time, and time minus start, and we'll see how quickly this goes. It doesn't like that. Oh yeah, it doesn't like start. Oh. Right, okay, we'll do print up here then. That was silly of me, wasn't it? So put that up there. Print answer and time start, and then we'll just call it down here. So p35 best there. Okay, let's see if this works. I'll just check my notes. It should do. See no reason why it wouldn't. Let's go for it. See how long it takes. 55 in 0.1 seconds. That's almost 8 times quicker than this one, and many times quicker than this one. So let's just run that again just to make absolutely sure. 0.16, 0.15, that's pretty good. Okay, so that's the quickest I could get it. So that will be it for today. Thank you very much for watching, and I'll see you next time.
Flutter by, butterfly, on velvety wings in the warm summer sky. Flutter by, butterfly, on velvety wings in the warm summer sky.